Okay, good. Good morning, everyone. So my name is Marco Cuturi. I work at Apple, and I'm also affiliated at ENSA Crest. That's a university in Paris. In both cases, I'm actually in Paris because I'm working in an office that's in Paris. And today I will talk about optimal transport. So you might have heard about optimal transport theory. This is usually very well known in math and applied math. As you might know, there was a Fields Medal given to Cédric Villani in 2010, in part for his work on optimal transport, and more recently another one in 2018 to Alessio Figali, also for his work on optimal transport. So optimal transport as an area in math is very well covered. What is quite exciting in recent years is to see that some ways to compute optimal transport now have improved, and so we can increasingly use those methods in data science. So to use those methods, first we have to be able to compute optimal transport and define what it is. So this is how it will go. I will present a few slides to explain. Maybe some of you may not be aware what the theory does. What is the goal of the theory? And then I will delve more on computations and a few applications. So let me just also say this is joint work with a lot of folks. It's quite exciting because many of those people come from different backgrounds. So we have, among those colleagues, I have people that come from, I would say, math, CS, optimization. Other people come from more biology because we have a few nice applications to biology going on. And so we are also developing toolboxes to help you experiment with optimal transport. And one of those toolboxes is called OTT-JAX. This is the logo there on the lower right. So OTT stands for Optimal Transport Tools, and JAX, maybe many of you might know what it is, but if you don't, think of it as another type of PyTorch or TensorFlow, which was developed a bit more recently. So let me just start with a very simple canonical problem that I'm sure all of you are familiar with, or I've at least heard about, which is this optimal matching or optimal assignment problem. So let me frame it in an abstract way. I am given two sets of points, okay, reds and blues, let's say. And for convenience, I have denoted the red points x1 to x5 and the blue points y1 to y5. So notice the number of points is the same. Out of those points, I would like to find a match, essentially a way to associate one blue point with one red point and one only. So how can I think about such matches? Well, typically you would use a cost function that would tell you how 2 points are basically what would be the cost of matching one red point with another blue point. And from that knowledge, those two things, the sets of points and the cost function, you get, or you try to compute an optimal permutation or matching. So how does this work? Well, first I have, as with any optimization problem, I have to define an objective function. And here my objective function is going to be the C of sigma, where sigma is a permutation, okay, any permutation of that set of 5 items. So there's 5 factorial possible permutations. And for any permutation, I'm going to score its, I would say, quality with this function, which is the sum of the distances that or the costs that I incur by matching xi with y sigma I. And so that pair xi y sigma I, basically I'm proposing to match them together, and then I pay a cost, and of course I'm going to pay that cost repeatedly over all possible all of the xi points there. So if you think about this, well, first let's start with any permutation here. So here this is permutation associating x1 to y3, x2 to y2, etc. And you can see visually that if the cost, for instance, is the distance between the points, this is a fairly bad assignment because it seems to be moving points far away from each other. So we can start thinking about different assignments like this, and of course the goal is to find the one that would be the best one. Let me just maybe say something though, which is at this point there is a very important and very, I would say, a fundamental limitation of optimal transport theory, either a limitation or a feature, a defining feature of optimal transport theory, which is that optimal transport theory will be there to study problems where we have something called mass conservation. So let me explain a bit what I mean by that. It means that if you, for instance, wanted to match the red points to the blue points, but you had no limitations on how many red points can go to a single blue point, and you had no concern that some of the blue points, for instance, are not associated, then we can solve that problem using nearest neighbors. Okay, so it's a very simple principle. If suppose, for instance, the blue points are users, sorry, the red points are users, and the blue points are are bus stations. If you want to assign users to bus stations, well, it's okay to think that maybe many users will use, you know, the same bus station, because maybe you could hope that a bus could basically take 3 people. And so in that case, if there is no notion of conservation of mass, I will explain a bit more what I mean by that, but like this bijection constraint does not exist, then of course the problem is very easily solved by a nearest neighbor assignment, or like a lowest cost assignment here. What optimal transport will be about is really to find for something that has a low cost, while at the same time, you know, satisfying this bijection constraint, which here is naturally given by the fact that I'm limiting myself to permutations. So of course, this is not a permutation, but I think more fundamentally, philosophically, what this means is that this is not okay in situations where you need one-to-one matching. So for instance, if those were, you know, taxes that were available at some point in time, the blue points were taxes and the red points were users, maybe, you know, a taxi can, any of the users could go anywhere, and so we need 1 taxi per user. So of course here the goal is to get the best possible permutation, which I am abusing a bit notations because I'm writing argmin. As you know, equals argmin means that in theory the solution should be unique. This is not always the case, but let me just, you know, gloss over that detail to say that I'm looking for at least 1 permutation that achieves the minimum over all possible, you know, assignments. So before I think a bit more about what I mean, but the problem, the first thing I'd like to say is that in terms of computations, this is a problem that's been around for as long as optimization exists. For objectively, even before. People can solve this optimal assignment problem using the so-called Hungarian algorithm, which was named after Hungarian mathematicians of the early 20th century. And more recently, another algorithm was proposed to solve it in the 80s called the auction algorithm. So we're talking about a very, very fundamental problem here. Both those algorithms, however, have limitations in the sense that they can only work, they will require, in the worst case, n cubed complexity. So if the number of points n that you're trying to match is, let's say, 10,000, you will already starting, you know, to have a hard time doing this optimal assignment. The other question I'd like to, the other point I'd like to raise, because this is an introduction, is why care about this? Well, there's lots of problems where this type of assignment, of course, reflects, let's say, an operational constraint, a real constraint. So the canonical example for optimal assignment problems comes from this worker and task assignment. Imagine you have, let's say, 10 workers that show up in the morning. You have 10 tasks, you have scheduled 10 tasks on that day. Every worker has a slightly different skill set. Every task will require a slightly different skill set. Your goal is to have all of the tasks completed by the end of the day. What would be the best way, you know, in terms of making it easier for the workers to fulfill the task, to do the matching? And here we can see obviously that there's this bijection constraint that appears, because you cannot put 3 workers on 1 task. That might speed it up, but on the other hand, there's going to be 1 task that is not going to be fulfilled. So this is a very typical problem. I would say that in machine learning and data sciences, this will arise, But there is also another context in which this arises a lot, and it's the notion of computing distances between distributions. So shift a little bit the gears, forget about the workers and tasks example, and think more about, blue points and red points are samples from some probability distribution. And maybe you would like to compute a distance between the probability, those two samples. So this was mentioned yesterday in the lecture on the Stein method, for instance, which was one possible way of computing a distance between two distributions. Here, the cost of this, the best possible assignment you can find, will appear repeatedly in statistics, and people call this, in a slightly more restrictive setup with assumptions on the cost, the Wasserstein distance between probability distributions. So I would say the OR perspective is trying to find an assignment. I will show some examples in ML. Then there's this metric, notion of being able to score, to quantify how far two samples are. And then there's a third one that I'd like to, I'm a bit disturbed by the static. The static is going to be like this forever. So the third one that I'd like to introduce is, I would say, a more physical, slightly more physical perspective on this. So suppose I am given with particles, 5 particles, and there's nothing that I can actually, I have a hard time distinguishing one particle from the other. Maybe because those particles are very small, or because I cannot tag them. Or maybe it's just, let's say, people that I look at, an altitude of 100 meters above, so I just see dots basically moving around. I can't really identify the particles individually. So suppose I'm, at one point in time, I have this snapshot, 5 points, and because I can't keep track of the particles all the time, maybe this is very costly in experimental sense, for a little while, I won't be able to look at the particles. I won't be able to follow them very closely. So the camera goes off, for a few seconds, and the particles during that time are evolving, they're changing. So here they might be moving around, let's say. And so at time t plus epsilon, I have the same particles, but I don't really know exactly who went where. I might try to guess, and this is going to be the goal of optimal transport. Because in the absence of this, I can't really reconstruct a likely trajectory for each of the particles. And so this is the game in optimal transport, is to say, well, this new sample of 5 points, the red points, I'm going to give it now a different name. I'm going to label them y1 to y5. And here my task will be, if I was nature, given that I started from the red configuration and I am now a few instances later in this blue configuration, what could have been, the most likely displacement of those particles? And so this is what optimal transport tries to do. It will tell you, well, if I'm looking at the particles at t and times t plus epsilon, maybe the least energy that you could spend to move the particles so that they reach this new configuration is essentially given to you by this possible displacement. So this perspective is increasingly used in sciences and data sciences. So let me just try to go a bit closer into actually what will be the subject of this mini tutorial, which is a relaxation of this problem. So why do we need to relax this problem? Well, it's quite obvious if you look at this setup that if my model is always going to be that I have a certain number of particles on the left and exactly the same number of particles on the right, and I'm not allowing any difference in sizes, this is not flexible. So you can start thinking about hacks to get around this. So suppose I'm giving the blue set, let's say 1,000 points, and the red set is like 673 points. I might start discarding or resampling and things like that, but that's not really very clever, right? So the very natural relaxation that people have proposed is this so-called Kantorovich formulation of optimal transport, which is as follows. it basically will start from the same idea that we have two families of points, except now we are no longer assuming they have the same number, the same cardinality, and even better, actually, we're going to assume that they can be weighted. So this is taking more like the probabilistic, we look at those sets of points as the probability measures. So we're going to follow maybe some of the particles have higher or lower mass. And so how can we walk through the same intuitions that got us to this optimal assignment problem with this slightly more generic setup? Well, it's actually not so obvious, at first sight, because of course the limitation that you have is that if you do assignments like this, well, first, sometimes you might not be able to cover the mass that you intend to. And more problematically, and this would more likely happen, if you have a big particle red and you pretend that it went to this particle here that has a lower mass, how do you account for this loss, basically, of mass? So if conservation of mass is still, this defining principle of optimal transport, we need to get some workaround. And so this is why we relax permutations using matrices, and it's a very natural relaxation, because if you remember, any permutation can be uniquely described as a permutation matrix, which is a matrix which has binary entries, and row sums and column sums are equal to 1. So there's only one item in the matrix per row and per column that has a 1. So how does that work? Here is a bit the physical intuition about this. I am going to list, somewhere with an arbitrary order from x1 to x6, the masses that are in the red measure, and I'm going to collect, the masses the same of the blue measure. So this gives me just two sets of masses. So you could call them histograms, okay, because they're completely unrelated to the points, to where the points were lying. And so now I'm going to look at matrices that have exactly, as rows, the number of red points, and as columns, the number of blue points. And here is the solution to relax permutations that I would propose for this weighted setting and different sizes, is to say, well, I am going to transport red mass onto blue mass, and I'm going to tell you for each of those red points where the mass should go. So imagine, for instance, I start with, let's say, this point x2, and I take a mass of x2, a chunk of the mass of x2. So this is a quantity that is a bit smaller than the weight A2 that was assigned to that point. And so essentially this little chunk, this area here, is going to be, appear here in this matrix, and this stands for the fact that I am sending part of the mass of this point here to this blue point there. So, okay, so when I start doing this, what you can see is that, okay, I've sent a bit of the mass of this. So you could see, for instance, like this red mass here, this is another very typical explanation of optimal transport. This might be, for instance, let's say, the blue points depict factories that produce some goods. Each of the red points. The red points depict factories, and each of those factories produces goods in a different quantity. So some factories are bigger than others. And so these goods need to be sent to the shops that are going to sell them to the consumers. And again, the shops have varying sizes. Some of the shops are bigger than others. And so I need to find basically an allocation that tells me precisely for each pair of factory and shop what is the amount that is exchanged. So you think those might be televisions, for instance. The red dots are factories producing televisions, and this is a total production of, let's say, 1,000 TV sets, and this is sending 800 of them to this shop. So once you have started, sending some of that production, of course, then you can start, dispatching this mass, this production across several shop locations. And so the game will therefore be to do this repeatedly. You can do this iteratively in this case by just filling basically the demands of all the shops and all of and satisfying the production of every factory. So what have we done here by this? We have essentially done a few things. First, we have constructed a matrix that has the same number of rows as number of factories and the same number of columns as number of shops. And it's quite intuitive that the entries that we put in those matrices are non-negative because those are quantities that we're transporting. So this cannot be, this is non-negative. This cannot be a negative number, of course. And the other thing that we have basically managed, or we have to, is to provide that this matrix has the quantities that actually are in agreement with what were the initial production and the target allocations. So the row sums of this, the row sums of the matrix have to sum up to A, and the column sums need to sum up to B. Now, once this is done, we have just extended this permutation setup by saying that the cost of such an allocation is going to be equal to the sum of the entries of this matrix P. Remember, this matrix P at the entry ij is telling us how much production from factory I goes to shop J, and multiplying this by the cost that it takes to go from factory I to shop J. This could be a shipping cost, this could be a cost in terms of gas, this could be a cost in terms of time, this could be whatever. We don't really care. As long as you tell me how much it costs to ship 1 unit of goods from I to J, this is what I'm doing. So the cost is this C of P, and just like what we did earlier, our goal in optimal transport will be to find the best possible matrix that minimizes this. So a bit of a historical note here. Again, I was telling you that optimal transport is one of those problems that's been around for at least now 80, 90 years. This is because this appeared essentially right before World War II. And you can imagine with this example of factories and shops that you could generalize it to, let's say, troops and battlefronts. I mean, logistics essentially appeared in World War II, and clever logistics requires planning, and planning requires optimization, and optimization is basically this. So this problem was first formulated concurrently by people in Russia, in the Soviet Union, and in the US. So the founding fathers of that theory are typically Tolstoy in the 30s in the Soviet Union, and then of course Kantorovich, who got the Nobel Prize for formulating this. He got the Nobel Prize in the 70s, but wrote about this as early as 39, 40. And in the US, names that you would attribute to this are Hitchcock or Kopmans, who got also the Nobel Prize in 75 for that work. And so we're really talking about fundamental econ. The principle of doing those matchings in a clever way is really deeply ingrained in those ideas. So now this is the, I would say, the operations research perspective, the optimization research perspective on the optimal transport problem. And how can, I mean, a question you should ask, a bit like when I presented this Hungarian algorithm, is how to compute this, since this is one of the topics here. Well, it turns out that this is a linear program. This optimization satisfies, exactly the definition of a linear program. It's even a canonical linear program. We are essentially looking at a space where we have matrices, but matrices can be seen as very long vectors that have non-negative constraints and have linear constraints. And we are optimizing a linear objective, therefore this is a linear program. So as far as linear programs go, we have, of course, a few methods, like the simplex method, to solve them. But here, it's actually a very specific type of linear program. It's one where the constraint matrix has a very peculiar property, which makes life a lot easier. And so this was understood in the late 40s, that this is not only a linear program, but a very nice linear program. And as a result, this has nice computational properties. So in a sense, if you were to run a linear program on that many variables, nm, it could be a lot more expensive. But because this is such a nice, simple problem, we have very efficient algorithms. So this is the half-full version of the story. I'm saying they are very efficient, but they are very slow in practice still, because we are talking about dealing with a cubic time in terms of the number of points that we want to match. So this is obviously a huge limitation for applications. And this is why there's been a few proposals to speed that up, and I'm going to discuss a bit those proposals today. The first one is about adding a regularization to this linear program. And as you've probably seen in so many of your problems, typically adding regularization to an optimization problem helps, and it sometimes helps either by encoding a prior knowledge or by making computations easier. And this is one of those cases. Here the computations are actually much better behaved. I will explain a bit this. So let me explain a bit the intuition. We are going to add a strongly convex penalty on the minimization that is given here. So we're moving away from the math, of the 60s, sorry, the 40s and the 50s, more towards the math of the 60s and 70s, which is basically taking advantage of convex problems. So this gamma here is going to be a regularization strength, and I will show that when you introduce this regularization, which is the entropy of the coupling P, you get something that is, I would say, for our purpose, quadratic in the size of the measures, or even faster in some cases. Of course, this is a bit like comparing apples and oranges, because I'm telling you that a regularized problem is much faster, but of course it's not computing the same solution. However, for practical purposes, this gap, from going to cubic and to quadratic is actually most often really worth it. And I will explain also for other reasons that for statistical reasons is actually, as usual with regularization, it also makes sense to do that for purposes that are not only computational, but other things. The other thing that I would like to briefly mention today is a slightly different approach, which we proposed more recently, which is to regularize this, or to be a bit more explicit, to constrain the problem further. So rather than adding some regularization, our recent proposal was to add some constraint on the rank of P. So I should probably be a bit careful here. This is going to be a non-negative rank, not just a regular rank. So I should probably put a small rank plus, but I will show later on that what I mean by this. Essentially, it's going to be a way to go further away from the permutation, mindset. A permutation matrix has full rank. This extended relaxations, of course, might have a large rank. What we'll try to do is look for solutions that have small rank. And the final, slide in this small intro is about computing optimal transport in, I would say, the setup that mathematicians care mostly about often, which is the continuous setup. So what do I mean by the continuous setup? So first I'd like you to notice that if you look at those points, the red points here and the blue points, they come from somewhere. And in machine learning, typically they come from a probability distribution. And so it's important to consider the case where we are thinking we have access to an infinite supply of samples, or a very large number of samples from two probability distributions, and still want to formulate a notion of optimal transport between the two. So in that setup, which is like the more ideal setup that has been the most studied by mathematicians, the problem is slightly different. It looks a lot more like the permutation problem, in the sense that rather than look for a permutation or a matrix, I will actually look for a map. And so, I'm sorry, I think I wanted to. Anyway, so rather than looking for a permutation, I will look for a map that will basically map every point in this red measure onto points on the blue measure. And so one of the biggest findings in mathematics, I would say, around that topic is that this type of problem where we try to find a mapping that goes from the red measure onto the blue measure, and that we will call T here. This is a transport map. We might look for mappings that are fulfilling two desirable properties. The first one, and I'm summarizing this with this push-forward notation, is that every time I apply T of x to a point x, I will land in a different location. I will look for maps that take input points and then bring them to target points. And I will try to look for maps that can reconstruct this blue measure out of the red measure. And the second thing that I would like to achieve is to make sure that those displacements, taking from those points x to T of x, are small on average, or at least have a small cost. So it doesn't take too much energy to move a point x to a point T of x. So this formulation here is what people call the Monge problem. So it's finding among all possible maps that take vectors and bring them to vectors, such that they basically push forward the red measure onto the blue measure, try to find the one that has, on average, the least displacement cost. Now, as I was saying, this problem is called the Monge problem because it was first formulated by a mathematician called Gaspard Monge in the 18th century, late 18th century. And for many, many years, for at least 2 centuries, this problem was posed, but not well understood. And we had very little insights on what the solutions were for that problem. This changed when around the late 80s and 90s, a mathematician called Jan Brenier came up with a few very important discoveries. So I would say this order here is a bit reversed. The first result was this Brenier theorem, which is the following thing. If your goal is to find an efficient way to transport a probability distribution in RD onto another, and the way you're scoring, the cost of this transport is a squared Euclidean distance, then what Brenier found is that no matter what the distributions are, if the input distribution, let's say it's continuous, the best way to transport the measure into another will always be necessarily to follow the gradient of a convex function. So you just need to find a good convex function that transports a measure that you're given into another that you're given, and this tells you that you should be fine. You should have an optimal solution. So this was Brenier theorem, and this was used by Brenier and a colleague Benamou to come up with a numerical scheme, since we're talking about computations, that works but in very low dimensions. So for many years, this route, I would say, was a bit neglected in the computational machine learning, let's say data science areas, because this worked for low dimensions. So there were some applications where this would be useful, but for applications that, let's say, that were like in dimension 10 or 15 or 50 or 100, this was not useful. And so this has changed in recent years because a couple of people have re-injected, the usefulness of neural networks into that problem. So what they did was to parameterize neural networks, convex functions as neural networks. This is called an ICNN. So this was proposed in an ICML paper in 2017, independently of optimal transport. This was proposed to provide, convex families of neural networks that were convex in their inputs, and hence the name ICNN. And this was used by Makova and co-authors and Corotini co-authors in 2020 to propose a clever scheme to parameterize those convex functions in this Monge problem. So I will detail a bit later how this works, but let me just essentially try to give you an idea of how this operates. The first thing that I will describe a bit later is that this optimal transport problem that you can describe in terms of maps, you can show that it has a tight connection with a so-called dual optimal transport problem. And so you can recover a solution for T star by parameterizing it as a different function f star. And that function f star needs to satisfy this equation. It has to be the minimum of some integration of f, the Legendre transform of f plus f itself on the second measure. So in other words, using a few duality theorems, you can fall back on this type of optimization problem to solve this thing. You will get that the best optimal transport is this gradient of this f, given that f is the solution of this. Here we have a problem, which is that, of course, for an arbitrary function f, and especially a high dimensional one, it's very hard to compute the Legendre transform. And so what people have proposed is essentially workarounds for this. So rather than having a infimum of only one function that is convex and parameterizing its Legendre transform, they use like a kind of auxiliary variable, penalize the fact that this variable is far or not from the Legendre transform, and run SGD on this. But I will go a bit more into the details of this later in this presentation. So this basically, yeah, this is where the animation ended up appearing. Sorry. So this was basically trying to illustrate, you know, the optimal the notion of maps between the action of a map T on the measure. Okay, so to summarize, what I will cover in this short course is two routes to modify the LP problem and run optimal transport at scale. So the first one would be this entropic regularization approach, and I will introduce this low rank factorization approach for couplings. And in the second part, I will basically talk about the Broglie theorem and explain how we can use neural networks to solve this more advanced problem that is of interest for measures in higher dimensions. And if I want to take a step back here and compare the left and the right, there's one thing that, you know, should be obvious, is the left one is a problem that tries to find associations between two samples and does not provide you with out-of-sample extensions in a way. Here, I just have a bunch of x's and a bunch of y's. I tell you which x's are associated to which y's, but that doesn't tell you if I have a new point that comes after that, where it should land. So this is I would say, a defining feature of the left problem, whereas the right problem has as a defining feature that we're able to extend this to out of samples. You can try to estimate it with samples from red and blue measures, but you can also use it later on to transport points that will appear after you have been given samples. So if I then fall back on this first formulation, I have this, I would say, canonical problem where I have a measure that has red points, red masses, encoded as AIs, those are the weights, XIs, those are the points. This is my input measure, and then I have a target measure which has BJs and YJs. BJs stands for weights, and YJs stands for locations. And so I will try to come up with an efficient way to transport those particles. By the way, let me just say, I also want to say, please feel free to interrupt me anytime if you have questions. This is not very clear. I would be very happy to take questions during the talk. Otherwise, we can also have questions during the break. So once you have posed this problem, if you remember my introduction, essentially it's as if the problem was split in two parts. One is about the masses, which are going to define how those transportation matrices look like, what are good transportation matrices. And the other is about the geometry, or I would say the cost structure that I'm applying on the points. So you abstract out two things, it's how mass is distributed to help me constrain those matrices. And the other thing is how are the points located, and this helps me construct a cost matrix. So this is the first, this is the geometry, if you want, of the problem. Here I'm just telling you how far each point xi is to each point yj. And here, this u of ab is going to be a set of matrices that makes sense, given the weights that I gave you in the samples. And again, remember that what those weights are for First, they define the size, of course, of the matrix, but they also tell you, well, the matrix should have row sums that sum to A and column sums that sum to B. With that in mind, it's quite common to call this Wasserstein. It's a bit of a abuse of notation because this is actually the Wasserstein distance only if and only if the cost is a distance. But let me just call this W indexed by C for the cost of the two measures. And this is going to be the minimum of all matrices with row sums and column sums, row sums and A and column sums B of this dot product between matrices. So here, of course, this is just the sum of the Pij cost between Xi, Yj. So earlier on, I told you this was a very classic linear program. And if you remember, whenever we have an optimization problem, and notably a linear program, we can define its dual. Here we have a linear program that is has non-negative constraints and linear equalities. And so it's very simple this is called like a standard linear program in standard form. It's very easy to write an equivalent dual linear program. So what does the dual linear program look like? Well, the dual problem basically says that here we had n times m variables. This was this matrix P. And the matrix itself, apart from those non-negativity constraints here, had two sets of equality constraints. Each equality constraint here, this is n linear rows, and then this is m columns. So we have n plus m constraints. What duality theory will tell you is that that part which you use to constrain the problem will appear in the objective of the dual problem. And that part which you were using to formulate the objective of the primal will appear in the constraints of the dual. So you're flipping, upside down the problem, grabbing whatever you had in the objective of the primal to make it the constraint, and what you had in the dual to make it in the constraint of the primal to make it objective in the dual. And here is what the dual problem looks like. It is going to be an optimization of n plus m variables. That was a set of the constraints, size of the set of the constraints here. And the optimization is basically maximizing the dot product between alpha, vector alpha, and the histogram A, vector beta, and here histogram B. And the constraints, as I told you earlier, they will be essentially defined by this matrix, and that will be this. We have those constraints, which are that the prices, those vectors alpha and beta are often called prices or potentials, are such that alpha I plus beta j is smaller than the cost from xi to yj. So let me try to give you an intuition on what this means, what duality means here in this particular setup. Imagine the red dots stand for, let's say, bakeries. They produce some amount of bread, and so they have to ship that bread every morning to restaurants that will serve it to their customers. And suppose I am a conglomerate, I own both the bakeries and the restaurants. Those are the locations of the restaurants, the red, and those are the locations of the bakeries in blue. Each bakery produces a different amount of bread. Each restaurant requires a different amount of bread, but because I've been planning carefully, the total amount of bread produced is the one that is needed by the restaurants. Now imagine I run an optimal transfer problem because I'm a careful planner, and I find out that the best way to save money to ship that bread to from the bakeries to the restaurants is pictured here. It's essentially going to say this bakery here is going to ship a little bit of bread to each of those restaurants, etc. So this is the primal problem that you have here. Okay. The dual problem, this is a slightly different story, is the following. I don't want to run this. I don't have a linear program solver at home, and so I just want to delegate this to a shipping company. And I tell the shipping company, well, please take care of the bread. It needs to be delivered from the shops, from the bakeries to the restaurants. And the shipping company will come to me and tell me, well, here's the deal. I will charge you for every bakery a given price to pick up a unit of bread, and I will charge you for every of your restaurants a given price to deliver a unit of bread there. You won't need to take care of, you won't need to think about how the bread was basically dispatched around, but it's just that the pricing scheme is basically you pay when I pick in the bakery and you pay when I deliver in the restaurant. 1 unit of bread. So in that scheme, what I will need to pay as the conglomerate to this shipping company is this quantity. It's going to be the price for each bakery to pick up 1 loaf of bread times what is basically produced at each of those locations. So the price will be different from bakery to another, plus the price that I will use for every restaurant times what is needed by the restaurant. So this is basically the total bill that the conglomerate will need to pay. Now, what is the interest of the shipping company? The interest of the shipping company, of course, is to maximize profit. So we try to look for a large bill here. Of course, the conglomerate doesn't want to pay too much of a price. So what is the conglomerate going to do? It's going to say, well, okay, you gave me this set of prices, alpha I and beta j. So let me just do something. For instance, if I look at, let's say, bakery number 1 and restaurant number 3, you're charging me alpha 1 plus beta 3 right now to pick a loaf of bread in the bakery 1 and deliver it to restaurant 3. Is this in agreement with what are the market prices to ship those items? And so if I look at this, well, of course, I want this to be validated, right? I don't want to be paying more than what FedEx, for instance, let's say, would charge me for just doing that. And so here is the dual problem. The dual problem is the tension between trying to maximize the profit for the shipping company, while at the same time, the shipping company knows that it has to be careful and not produce a set of prices that are a bit too extravagant. So this is this dual perspective on the same problem. And let me just also say that if you look at this prices here, it's very easy for the shipping company to let's say, increase the price of pickup and decrease the price of delivery. Now, for instance, if I tell you, well, the price of pickup is minus $100, I'm going to give you, at this bakery 1, it's minus $100, but the price of delivery at another restaurant is like $101. Of course, this cancels out. This $100 cancel out, and so there's nothing that happens if the delivery company increases all of the alphas by a given constant and decreases them by another constant. So it makes sense to have positive and negative prices. Now, this is the solution of this dual problem on exactly this very same problem. Okay? And what this reveals is the following. I think there's two different perspectives, of course. Here is, you can see the actual routes, the displacements of the goods happening. Here on the right-hand side, I've pictured the dual vectors using a color map. And as I told you, some of the values might be very well negative. It doesn't really matter. But what really matters is the relative, order of those dual variables. So if you just focus, let's say, on the restaurants, the red dots here, you will see that the price to deliver in that restaurant here is much higher than the price to deliver in the other restaurants. Intuitively, this makes sense. This means that despite all of my efforts to find an optimal transport, essentially those items here seem to be a lot more costly to me in terms of bringing bread than the other restaurants. And here it's the same thing. Those bakeries that are here, I need to pay a price to pick, the bread there, and the price is much higher than the price we need to pay for those 2 bakeries that seem to be a lot more centrally located. So to give you a bit of intuitions, this is simply sensitivity analysis. If I am the conglomerate, I'm running my optimal transport, paying the price, etc. If I want to decrease this optimal transport cost, if I want to make it smaller, essentially there's going to be two levers that I can play with. The first lever is arguably maybe a bit difficult, is to move physically, spatially, the locations of bakeries or restaurants. And if you look at this solution, it's very obvious what you might want to do. It seems, for instance, this restaurant is awfully, far from the bakery that for now is the best place to ship the bread. So if I wanted to even reduce my transport cost, I would just simply, let's say, move along this line. The same thing applies here, for instance, for the bakeries. This bakery is very far from the others, and it might make sense, and immediately I will get a sense of how much money I will save. Imagine, on the other hand, I want to use the other lever, which is maybe a bit easier, which is the amount of bread that I'm producing. Well, it sounds very sensible to decrease the amount of bread produced here and maybe increase that which is produced there, and vice versa, because the prices right now for pickup and or delivery are much lower, respectively, in, let's say, those bakeries and those restaurants. So maybe I want to increase, the restaurant sizes there in the middle. So this will play a role when we are going to talk about, optimizing with respect to optimal transport. So geometrically, this problem looks like this. As every linear program, it's going to be a cost vector. So here we have to picture ourselves in a space of matrices, and a set of matrices here, which are defined exclusively by the weights. And what the optimal transport solver that I mentioned earlier, the simplex solver method, or min cost flow solver will provide you with, is, after a lot of work in cubic time, a best matrix. And the matrix, with probability 1, let's say, if your inputs are a bit random, is going to be a vertex of this polytope. So there's one thing that you should be careful with polytopes and linear programming in general, is that they can be a bit nasty, in the sense that the solution, this P star, I told you that in almost all cases it will be unique, but there are cases with very low probability where it might not be, and when that happens, essentially the solution jumps around. So in the context of end-to-end differentiable machine learning that we've come to use for pretty much everything now, this is an issue. Linear programs are an issue for that. And so let me just try to give you an intuition of why. Imagine I perturb a little bit my inputs. Remember the x's were what I had formed to, those were the points where my masses were located. If I perturb infinitesimally, there might be, very hypothetically, a case where this cost vector here will be orthogonal to a facet of this polytope. So without getting too much in details, what happens is that visually, as you can see there, the number of solutions is infinite. But I told you this never really happens in practice as long as your data is continuous. But what happens is that as you will perturb a little bit the entries, you will be jumping around from one solution to another. So what this makes, what this adds as a challenge is that if you are planning to use those optimal assignments or optimal matrices in more advanced machine learning pipelines, what you're left with is a P star which has no meaningful Jacobian with respect to the inputs x or y. By no meaningful Jacobian, I mean that if you followed a bit what I did, I perturbed a little bit x for a while and P star didn't change. Therefore, the Jacobian of P star with respect to x was 0. And then all of a sudden it jumped to a different solution. So it became infinite. More, I would say, anecdotically, this means that the Wasserstein distance that we like to compute to quantify, for instance, the difference between two point clouds is not really differentiable. But this is more like in the sense of the absolute value function. It's not differentiable, it has kinks. Having kinks for a loss is not that bad. But if you want to use this P star for something a bit more evolved, this is bad. So more, I would say, another hands-on problem with network flow solvers is that, I don't know if you've tried to implement them, they're actually quite challenging and do not parallelize well. It's very hard to run them on let's say, GPUs or take advantage of GPUs. So this is why somewhat there are a few issues, and this just to illustrate my point, this is an old capture of one of the solvers that are the most simple out there to solve this problem, which was proposed 20 years ago to solve the Earth mover's distance, and unfortunately it's still very much complicated at this point. So to summarize a bit, we have this problem, the optimal transport problem. We use it to compare two sets of points, or probably two measures. Very often in practice, because we are in data science, those samples will come from an underlying distribution. Typically, the distribution might be high dimensional or reasonably high dimensional. We're not doing graphics, where let's say we might be representing points as 3D point clouds. Here we are assuming we have measures. And so the question that I'm asking is, if we want to use optimal transport and we have access to samples, first, does it make sense to use that celebrated theory that people have received Nobel Prizes for a long time, or should we try to look somewhere else? So the first point that I told you is that if I have access to samples from two distributions, typically, if I really want to go this linear programming route, I will need to pay a price that is cubic in the number of points. The other aspect, which I think is more statistical, and I was referring to it in the introduction, is, okay, there are two underlying densities. I want to somewhat compare them, but I can only have access to samples. When I get the samples, I can solve this optimal transport problem. That takes a lot of time. Okay, I'm going to pay for it. But does it actually approximate in any meaningful way the quantity that I want on the underlying density? In other words, am I overfitting when I'm doing this computation? And this is what people call the statistical complexity of those Wasserstein distances. So the question would be, if I were able to compute the Wasserstein distance between the two densities, this W mu nu, and I'm given samples to approximate it on samples, how can I expect this quantity that I'm computing on samples to approximate this the true Wasserstein distance with respect to the underlying density? Of course, I know that when nm goes to infinity, essentially this converges. This is law of large numbers. It's going to be fine. But I'm a data scientist, so I'm not particularly convinced by a law of large numbers argument. I want to have an idea of what happens when I have, let's say, 1,000, 5,000, 10,000 points. And here, there's a very long series of works that goes, let's say, from the 60s to now. People are still studying this, that all point to a curse of dimensionality type result. So this is a bit informal because, of course, this will depend on the actual setup. What is the cost that you're using? Here, I'm still using this cost, so people will use, for instance, the square Euclidean cost, the Euclidean cost, various types of costs. But in a very generic setting, when you are in Euclidean spaces, it has been shown that you can prove that the cost, the gap here between this density true quantity, the population quantity here and the sample quantity, is only going to decrease at the rate of 1 over n, 1 over d. So 1 over d being the dimension of the space. So this is terrible, right? You are really paying the full price of dimension. And remember, I was telling you that people want to use optimal transport in dimension, let's say 50. So it's not, of course, a meaningful route to get there. So this is why one of the pillars, I think, of the recent approaches on computational optimal transport, and especially for data sciences, not for, let's say, graphics, is to regularize, in a way, include some inductive bias, some prior that will help you compute or approximate optimal transport. So in a way, it's a way of getting further away from the mathematical definitions to something that includes some meaningful knowledge to facilitate your estimation. So one possible route that I will briefly describe here is this idea of entropic regularization. So if you think about this set of matrices, this U of AB, You might remember that actually this set of matrices was basically a set of joint couplings. Those are matrices that have row sums and column sums that sum to A and B, but therefore, if you look at their entire total sum, it sums to 1. So this is like a probability distribution. And so it makes sense to think about trying to regularize the optimization and couplings with a quantity that makes sense for probability distributions. And in exchange, I'm willing to do, to change a bit my problem if in exchange I can get something that is faster, scalable, maybe easier to run on parallel hardware, GPUs, so using simpler routines than those that we find in combinatorial optimization. And there's another element that I'd like to underline here, is this notion of differentiability. I would like somewhat, to have a solver that outputs a P star that is going to be better defined, maybe uniquely defined, and has meaningful derivatives with respect to the inputs. So this is what we get using a entropic regularization. This is one possible regularization. There's been a few works that have explored other types of regularization, like L2 or various others. I think that a few years now, after those first papers, the consensus is that entropy works really nicely for both computational reasons and also statistical reasons. It's easier to analyze, and it actually works computationally very well. So let me introduce this, this P gamma. I will write it like this, indexed by gamma, because gamma here is the regularization strength of the entropy. So why does this work well? It works well because of that theorem, which is actually very easy to prove, which is to say, if I look at this problem, this is the linear program minus gamma entropy, and this is the constraints. The first thing that I can now say more comfortably is that this has a unique solution. This has a unique solution because the entropy is one strongly concave on the simplex, and so minus gamma times entropy here is gamma strongly convex on the simplex, so therefore there's a unique solution. So P gamma exists and it's unique. And not only that, if you just use the Lagrange method of multipliers, so really the most simple tool that you can come up with constraint optimization, you will find quite quickly that the solution P gamma must have a very specific factorization, and that factorization is as follows. There must exist a set of two vectors, so a pair of vectors, u and v. One is of the size n of the first measure, and the other is of size m of the second measure. And this P gamma must have this factorization, which is a diagonal matrix, K diagonal matrix. And this K matrix is a matrix that you get as a byproduct of your data. It's essentially the element-wise exponential of minus the cost divided by gamma. So why do I call this K? Because in many examples, for instance, when the cost is the squared Euclidean distance, this amounts to a Gaussian kernel. So we're basically going from cost distance matrix to Gaussian kernel matrix, between the pairwise Gaussian kernel matrix. So this is easy to get. So I can tell you the solution has this shape. Now, from there, I'm not very far from actually trying to solve the problem, because I know that this solution, the solution must have this shape, but also it has to satisfy the constraints. Therefore, it must be such that the sum of the rows of this matrix are equal to A, and the sum of the columns of the matrices are equal to B. So this means that if I reinject it here, this matrix times 1 is equal to A, so this is the row sums. This matrix transpose, so this matrix times 1 is equal to B, this is the column sum. And if I just do very basic algebraic operations, so for instance, a diagonal matrix times 1 is just a vector, like this. Then diagonal matrix times a vector is just scaling element-wise the entries of the vector kv or k transpose u. So it's just element-wise product of vectors. And so a vector times a vector equals to another is the same thing as saying the first vector equals to the ratio of element-wise of two vectors. So I'm just making this slightly more easier to write. So in other words, this regularization here amounts to finding two vectors u and v that satisfy the set of nonlinear equations. There are simple equations, yes? Yes. Yeah, which makes life easier. Yeah, actually remember that this matrix is even rectangular. So I'm not sure it would make sense but so it's element-wise, yes. And so these two equalities is essentially what we want u and v to satisfy. So what do we do when we try to have things satisfy this relationship? We just run a fixed point iteration. And the reason this is called Synchron's algorithm is because Synchron was the first in the 60s to prove that this fixed point iteration converged. He's not the one who invented it. These iterations were proposed in the early 20th century by economists who called it the RAS method, or later in the 40s by statisticians who called it IPFP, iterative proportional fitting procedure. But Synchron is the one who proved that actually this was a legit way to find a matrix here that had the right marginals, row sums and column sums. So Synchron algorithm essentially proposes to do something very simple, which is initialize this vector v, and then repeat iteratively, one after the other, those two updates, and then wait for convergence. If this sounds a bit ad hoc to you, and maybe you should find this a bit ad hoc, because it sounds a bit like a recipe, maybe there's another very simple intuition on what the Synchron algorithm is, which comes from a more, I would say, orthodox optimization reading or analysis of this. And it comes from the analysis of the dual problem associated with this regularized primal problem. If you remember the dual problem, I briefly mentioned this, there was this constraint that alpha I plus beta j had to be smaller than the cost of between xi and yj. Well, it turns out that if you compute the dual of this regularized problem, you get a dual problem, okay, which predictively looks a lot like the dual of the original LP. So we're still maximizing over two vectors of this cost matrix. But now the constraint is gone, and the constraint has been turned into this penalization. And you can think about this penalization as a soft penalization of this hard constraint that alpha I plus beta j is smaller than the cost between cost, or here the distance, probably which would be the notation between xi and yj. And so if you look at this, even though this was already nicer, because I walked you through this Synchron idea, this is actually much better. This is an unconstrained optimization problem, which is concave, because this term is concave. So it's just an optimization problem of two variables that is not constrained. There's a ton of approaches that you can think about to optimize it. Very simple gradient descent, LBF, GS, whatever. There is one simple approach, though, which works very well here, which is block coordinate ascent. Why is that? Well, because if you look at this this problem here, sorry, I think yes, no, if you look at this problem here, I won't go into the details. If you compute the gradient with respect to alpha of this energy, you get that you can cancel the gradient, make it go to 0 with respect to alpha by just applying the simple update. And if you do the same thing with respect to beta, you find out that this update cancels the gradient. So in a way, if you look at this dual perspective and reparameterize those vectors alpha and beta using this change of variables, you find out that canceling the gradients, doing this block coordinate ascent on the dual problem is exactly the same thing as doing the synchronous algorithm from the more primal perspective. So in other words, the dual looks at the dual updates of log coordinate ascent look a lot like log space, updates for the synchron problem. So I told you about this route to compute the regularized optimal transform problems. I don't have time now to validate more my claim that this is actually much more scalable and works better. There's lots of works that have been using the synchron algorithm to approximate optimal transfer in recent years. What I would like to show you is, I think, now something a bit more interesting, a bit more cutting edge, which is the idea that the synchron algorithm also helps you differentiate optimal transport. So by differentiating, let me just try to give a bit of intuition on what I mean by this. So if you take a step back, essentially what we're doing is computing distances or assignments between two weighted point clouds. And what I mean by differentiating that is I want to change either of the point clouds and predict essentially what the distance between the point clouds will become. And for this, there's two ways to do my perturbations, a bit like when I was talking about the conglomerate with the bakeries and the restaurants. Either I change the production quantities of restaurants and bakeries, so this is amounts to changing the masses, or I change the locations. So let's talk about changing the production, the masses, the quantities. So this would be like keeping the same points, growing or decreasing the size of each of those sticks. And what I would like to understand is what happens to my Wasserstein distance between the two point clouds after I have done the perturbation, and in what sense has it changed from the baseline, from what happened before the perturbation. The other, again, think about the conglomerate. The other possible alternative that I have is to now change the locations of the points. So this would be perturb, my locations. And here the same thing happens. I would like to have an idea of what could happen to my Wasserstein distance between the two point clouds when I run this perturbation. Of course, this is a preliminary to more advanced tasks, such as trying to formulate gradient descent to decrease the Wasserstein distance between a set and another. Not just computing it, but putting that as a loss function. Well, for both of those problems, it's actually quite easy to predict what happens when you change the weights or the locations, because we can resort to something called the Danskin's theorem. And I would try to, and this is valid clearly with the dual formulation. So let me try to remind you what the Danskin or the envelope theorem is about. So imagine that I am defining a function for a variable x. So x here could be my locations in the previous slide or the weights before. This is just a generic variable, x. And my f of x is this mean with respect to z. Z is a set of transformations or anything of a scoring function here, g, objective function of g of x and z. So I can also introduce, if my function g is well behaved enough, and I would assume this here, the argmin for that very same problem, z star. Okay? And so as a result, what I have is that you can say that if this is valid here, f of z is equal to this g of x, z star of x. Okay? So the question is, what are the variations of f with respect to x, given that x somewhat is appearing twice in this function g? What the envelope theorem tells you, and Danskin's theorem tells you, is that in that case, the gradient of f here is basically only captured by the gradient of respect to the first variable of g, computed with respect to x, and at z star of x. So in other words, you can almost act as if this was a constant quantity of x. So this works because I define f of x as being the minimum of something. So just to remind you of why we have this, well, essentially we have this because if you were to use the chain rule with respect to x here, well, x here this is the challenge, appears twice, right? It appears here and here. So the gradient with respect to x of this quantity should in principle be the gradient with respect to x with respect to the first variable of g, plus the gradient with respect to the second variable of g, computed at x z star of x, but corrected by the Jacobian of z star of x. So how does z star change with respect to x? Fortunately, because of this relationship here, this quantity here is 0 precisely because z star of x, z star is the argument and therefore cancels the gradient of g at the second variable. So this is like a very high level description of the Danskin or the envelope theorem. Yes? No, so it's going to be a bit more tricky, and so you have to look at the exact, hypothesis. But I'm just trying to give you a high level here overview of why this is the case. Here, of course, in everything that I'm showing here, everything will be differentiable. So, in other words, if you are in this setup, remember when I was playing my perturbation game? If I look at P star of A, X, B, Y, so this is a bit like the Z star that I was describing earlier, this depends on the inputs, is evaluated at a function of the inputs as well, and this is my transport cost. If I were to change a little bit the X, essentially what I'm telling you is that even if I was computing the P star at X plus delta X, actually that change would be negligible. Here, even in this case, it's actually a bit extreme. That change is 0 because P star hasn't even changed here. And so we get that the only source of differentiability, the only thing that is actually changing when I'm computing the gradient of the Wasserstein distance is simply the change of the cost function, in the cost functions. So, in other words, if you want to compute the gradient of the Wasserstein distance with respect to black square, here black square is pretty much anything you want, it's usually very easy. You just need to essentially freeze, the solution that you find, and then run directly, just differentiate the part that's not depending on the solution. What is more problematic is differentiating the optimal transport solution. This is a lot more pathological. Why? Because if you look at just simply this drawing here, what you have is that my Jacobian, how this P star is changing with respect to the inputs, here in the inputs, changes the inputs here is delta x, is actually very badly behaved. It's either 0 or plus infinity. And if you think about, running this in a deep learning pipeline, we all know that we need basically we prefer to have gradients that propagate, throughout the architectures. So therefore, one of the other, I would say, advantages of this regularized formulation, apart from being faster and also being more meaningful statistically, I didn't also delve too much into the details about the statistical aspects, but it's also proved to be better to have this regularization for statistical purposes. We have better sample complexity bounds. The other reason why you might want to regularize is because you can try to think about a smoother, if you want, trajectory of this P gamma that will continuously vary with respect to the perturbations in the X. So if you want to use optimal couplings or matchings in a deep learning architecture, this will be likely the only way to make this work. So I should probably conclude here, which is, if I show you those drawings, it sounds indeed better to aim for a solution which is somewhat in the interior of this set, regularized, because we expect that this Jacobian, how does this optimal transport matrix change with respect to the inputs, will have a more meaningful behavior. The question is how to compute it. Remember, my P gamma is still defined as being the minimum of something. So there was a workshop yesterday on algorithm unrolling, and so I think this is very much related to algorithm unrolling. What we want to compute is how does the solution of an optimization problem vary with respect to inputs. And there's essentially two canonical ways to do this. The first one is either algorithm unrolling or implicit function differentiation. And so let me just try to walk you through the two of them and explain a bit the advantages, the compared advantages of either. If you think about what I have proposed with this synchronous algorithm so far, the first feature is that the synchronous algorithm seems to be like a universal black box. You know, it's like it just takes into as inputs the points and the weights, and just runs this fixed point iteration. There's not even a gradient step, you know, that is involved. It's just you know, a workaround, like a very simple solution, very simple to implement, and it's so simple that it's actually a while loop basically. And so if you think about this as a programmer, you just implement this while loop, this fixed point iteration, and because you have limited resources, you stop it after a while. That makes a lot of sense. So what a programmer would think about this is, okay, just give me a vector to initialize my fixed point loop, apply the iterates one after the other, and after a while stop, and this is what I get in the end. What I call PL is what you get after L iterations. Now, how does PL vary with respect to changes in inputs X or A? Well, you don't really have to compute it by yourself. You can just delegate this to any automatic differentiation toolbox that will basically do algorithmic unrolling for you. And I should probably be a bit more specific. What those toolboxes are actually very good at is either, of course, instantiating this huge Jacobian matrix, but more to the point, they are able to provide like a linear operator that applies this Jacobian matrix to any changes in X, or the Jacobian, sorry, or the transpose of that Jacobian matrix applied to any matrix of the size of P. So this is basically backprop, you know, algorithmic unrolling. This requires zero effort on your end. This should be straightforward. The other approach is a lot more involved mathematically, but has a few benefits. So one of the things that I didn't really describe here is that for this to work, to have access to those Jacobians or those Jacobians applications, you need to store all of the intermediate values of your computational graph, which means here that you will need to store all of the U's and V's that my algorithm is computing on the way. So this can be a burden because sometimes the synchronous algorithm can require maybe 200 or 300 iterations to converge. So this can be a memory burden. The other way to get around this memory burden is this implicit function theorem perspective. So let me explain a bit what I mean by implicit function in this setup. You remember that my main problem, I would call this like the optimal transport problem or the WC problem, was to find two vectors alpha and beta that satisfied, that maximize this. And as the solution of some optimization algorithm that is unconstrained and relatively easy to solve, there's no pathologies, it suffices, as I told you, to just basically set the gradients to zero, verify that the gradient is zero. So the synchronous algorithm on this, remember, was just simply trying to cancel one after the other those gradients with respect to alpha and beta. And so when you have this energy, you can define a route map, basically, that basically tells you that you are at the optimum by simply stating that if I consider this map here H, which to all of those inputs and optimization variables alpha and beta outputs the gradient of alpha of that energy, then you get a vector valued map, which is of size n plus m. And what we know is that by definition, we have converged when that map here is equal to zero on the right-hand side. So this is going to be the root equation that we're going to differentiate to characterize the differentiability, or like say the variations of those optimal dual variables with respect to inputs. So here I'm just going to take the mathematician view. I will simply say I have converged. This is my map here. I've written it in a slightly different form. It's just saying that my dual variables satisfy those constraints that their gradient is 0. And I know that if I define my map f as being whatever you give me as input, I will output those optimal dual variables that characterize the optimal transport solution. And you give me this vector valued map that characterizes how far I am from the optimum, then that h applied on the inputs and of the optimal solution from the inputs is equal to 0. This is what typically we would differentiate. And so our goal here, if you want to differentiate optimal transport, is to understand how those things here, the outputs of this function f, vary with respect to the inputs. And so the implicit function theorem here is straightforward. It would be simply saying the Jacobian of the outputs, the Jacobian of the optimal transport result that I'm looking for, with respect to anything, this could be any relevant parameter that is basically included here, is going to be, this is just the Jacobian of this map here, the root map here, h, with respect to the variables alpha and beta, evaluated at alpha star, beta star, the optimal solutions that I found, inverse, so this is a linear solve, on the columns of this Jacobian with respect to this time the square thing that I want to differentiate against, applied again at alpha star, beta star. So this is the implicit function theorem, and it's very rare that we will want to compute exactly what that Jacobian is, because that Jacobian as a matrix will be very high, very large. Remember, it's a matrix of size n plus m times, let's say, whatever dimension of the input is, which could be x's, so this could be thousands of points multiplied by their dimension. However we want to use, and this is the defining feature of backprop, of course, or sorry, end-to-end learning, is that very often we will define a loss function, a composite loss function, which somewhere in the middle will leverage optimal transport. It will use optimal transport for some computations. And so there are a few examples in the literature of this that have been done in the last 2 years. I don't have the time to present use cases, but for instance, one which is quite successful recently is about soft sorting or soft ranks, soft smoothened rank functions. And so if you want to compute this gradient with respect to parameters that are themselves injected into the optimal transport computations, what you need to do, what you need to provide the algorithm with, in the spirit of backprop or a reverse mode differentiation, is to provide an operator that, given a z, can apply the transpose of the Jacobian of this optimal transport solution with respect to the square. And so this is where I think software, and I mean all of those, JAX in particular is really fantastic, is because although this looks quite complicated here in equations, it's extremely easy to implement in practice. So let me try to walk a bit through why this is easy. So I want to apply this transpose Jacobian of the optimal transport solution to any vector because I'm doing reverse mode differentiation. I know that on paper, the Jacobian of the outputs of the synchronous algorithm with respect to any inputs are equal to this thing. So if I just add a transpose here and a z on the right-hand side, I get that this goes to the left transpose and this goes to right with the transpose here. So this is exactly what I get here. So if you look at each of the blocks here, they're not as bad as they look. The first one is we have a linear system that takes as an input a linear operator. So it's not so difficult to solve this with, typically here in this case, conjugate gradient, by making calls to a function that is a linear operator and not to the matrix. Because we can actually call something called a primitive, which is in JAX, which tells me if you give me a map H, remember the map H is actually analytical, it's very easy to compute, it's easy to define. You can ask JAX to automatically compute the equivalent vector Jacobian product, which corresponds to the application of this Jacobian transpose. And then once you give me access to this linear operator, it's very easy to also call, a linear solver that is going to be in the linear sparse, space, but it's not exactly applying. I mean, it's not related to sparse matrices at all. It's just an implementation that allows you to solve a linear problem using just simply a function rather than a matrix. So once you've done this, you can then use JAX VGP again to apply this transpose matrix here. So in other words, you just define this H map that I wrote earlier, which is quite simple to implement, and then JAX does everything. So as a result, and this is a bit one of the illustrations that we do in this odd JAX toolbox, we're able to compute the Hessian of this optimal transport cost. Because remember that the Danskin theorem will work for the gradient, but it doesn't work for the Hessian. And so you need to have this type of second order differentiation. And so here in the toolbox, in the web page, I show basically applications where we compute Hessians with respect to the weights. So now, let me just comment on a few useful generalizations of optimal transport, especially if you are interested in applications. One very useful generalization is that of unbalanced optimal transport. So this was proposed about 5 or 6 years ago. And the idea is as follows. I mentioned earlier that, at the core of optimal transport was this principle of conservation of mass, and that you needed to find a matrix that has row sum and column sums that are prescribed. It turns out that you can relax that constraint to something that is less hard and more like a soft constraint. So a very natural, intuitive way to do this would be to say, well, maybe rather than having the row sums and column sums that match this, why not introduce this Kullback-Leibler relaxation? So in essence, it would be like saying, rather than saying that this is equal to A and this is equal to B, why not just add in the objective something that measures the penalty, the gap in Kullback-Leibler sense. So why Kullback-Leibler? Well, in the original formulations, there's all sorts of penalties that have been used, but one of the nice things is that if you add the entropic regularization to this penalized, constraint of mass conservation, what you have is an extremely easy algorithm, which is a synchronous algorithm, which is very slight modification. So let me just try to explain a bit. Before this, you could think that this value row here was infinite if you wanted to be constrained, because you don't tolerate any deviation in Kullback-Leibler sense between this matrix marginal and the marginal they are given. But if you introduce this penalization, you are going to do the synchronous algorithm as we were doing it before, except that now you're going to apply an element-wise exponential to the vectors of the update. And the element-wise exponential is just rho divided by rho plus gamma. So it's going to be strictly smaller than 1. So it's very easy to recover that when rho goes to infinity, those exponents here converge to 1, and so we fall back on the original synchron algorithm. Here we have something that is a bit in between. It's going to produce a matrix which will be a coupling, but it won't have the right mass basically. It will deviate a bit in row sums and column sums from A and B. Let me now introduce very briefly this other regularization approach that I was discussing, which is about trying to come up with a rank constraint with the optimal transport problem. So let's forget for a second about entropy. Let's completely forget about entropy and or Kullback-Leibler regularization of the marginals, etc. Let's go back to the original optimal transport problem. So this problem here is minimum of P, matrix, row sums, column sums, and the cost. And what I am going to introduce instead is a factorization for those matrices P that will have a low rank. So what does it mean that I want the matrix P to have a low rank? Here it will be low rank in the following sense. Remember, I have a matrix of size nm. That's my coupling that basically measures the strength or the association between h point xi and h point yj. I will parameterize it explicitly as the product of three matrices. The first matrix is going to be a matrix Q here. It will be of size n times R. This will be a matrix, square matrix R, and it will be diagonal. And here will be another matrix, big R, which will be small r lines and m columns. And it turns out, I'm not going to show it now to prove it, but you can believe me, that if you introduce a first matrix Q which has that shape and which satisfies row sums A, column sums G, and another matrix R which satisfies row sums B and column sums G, and G is in the simplex, so G is itself a histogram of size R that sums to 1, then that thing here is a matrix with row sums A and column sums B. So it's a bit as if you were factoring, you're providing an explicit factorization for this coupling matrix here. So going towards statistics, this is related to the minimal. If you have a matrix P here that you can factorize in this way, it's related to the number of latent variables that you need to parameterize, the smallest number of latent variables you need to parameterize this coupling matrix here. There is a more efficient factorization of this joint distribution. And so we draw inspiration from this factorization to basically say, this is the original optimal transport problem. Can we define a optimization, a transport problem which is now constrained on the space of couplings that have a non-negative rank that is up to R? And this is essentially what we do here, or exactly R, sorry. And here, this is exactly what we propose. So you can find some intuitions for this approach in a paper by Foro et al. In 2018. And our paper with Meyer, Sedbon, and Gabriel Perret provided a more general approach for this. And so this sounds like at least smaller optimal transport problem, of course, because we have far less variables. And so what we show is that in the spirit of alternating optimization, so here to be more precise, the Dijkstra's algorithm, we're able to solve this problem with respect to the three variables in an alternate fashion. One of the drawbacks, of course, is this is no longer convex, so we have to initialize this carefully. But we have been seeing very good performance about this. And why is this a succession of simple optimization problems? Because if you only optimize with respect to Q, you can very quickly see that this problem is of size n times R by just putting all those matrices on the right-hand side. If you optimize with respect to R, of course, is again a problem with respect of size m times R. And if you're only optimized with respect to G, this is just a problem that only depends on the vector itself. And to be a bit more, to give you a hint of how we do this numerically, we actually still fall back on some notion of optimal or regularized optimal transport for computations, because then we add some notion of entropy on each of the components Q, R, and G. So I'm not going to show results on this, but we've pushed this in recent applications, and we're able now to compute optimal transport between 200,000 points, 300,000 points, between pairs of measures of a fairly large size. So before I go very quickly into the second part, is there any question maybe on what I've, yes? Yeah, so this is a good point. I would say there's no intuition on why it should be low rank, because if you really follow the true, if you believe that the linear programming formulation of Kantorovich is the ground truth, those matrices will never be low rank, except in very pathological cases, like where there are some duplicate points or like distances that are equivalent, etc. But fundamentally, you will never have a optimal transport, the result of a linear program solver. In this case, there will be low rank. Just like when we added entropic regularization, you will never have a solution that will look like something that is entropic. We really rather than regularizing, we're actually modifying, I guess, the structure of the solutions. But what we're hoping is that by adding that rank constraint or the entropic regularization, we're adding interesting bias, to the objective, and coming up with solutions that might be more stable with respect to inputs. So that's it's not that we're trying to re-hack our way, and find that an optimal transport solution will be low rank, because that's not the case. It's more like we want to go away from this vertex corner. We think it's better to move towards something that is more, first, maybe scalable, and also better behave with respect to inputs. Here, what I have to say though is that we don't have yet the differentiability. At least on paper, it's not so hard to get there, but numerically, and I would say computationally, it's not that as efficient as the synchron approach. Thanks for your question. Okay, so if there's no other question, let me just try to go a bit towards this, the idea of using neural networks to. I'm going to shift gears completely and propose a completely different route to computing optimal transport that is not using the sample perspective, sample points to points, but more like densities. And as a result, I need to introduce continuous notations. So the notations are continuous mostly because we're going to deal with densities, but they're exactly reflecting the same intuitions that we have in finite sample settings. So in the beginning, I told you about this Monge problem, trying to find the map that sends points from the first measure to the second measure. It guarantees that you recover the good measure in the target, but also has low average displacements between x and t of x. It turns out that this Kantorovich formulation for couplings, the intuitions where we have matrices that have row sums and column sums, etc., it translates directly to continuous couplings. So rather than having matrices, it's just going to be a density or joint density that has the first marginals, which is mu, and the second marginal, which is nu. It turns out that just like in the finite setting, we also have a dual problem, a continuous dual problem. And so now, instead of being just simply alpha transpose A, it is going to be a test function phi integrated against d mu, test function psi integrated against d nu. They have to be, you have to be able to integrate them against those two measures. And then the constraint that alpha I plus beta j smaller than the cost is now just simply for every point on the support, phi of x plus psi of y is smaller than the cost between x and y. I will use this notation because it's slightly handier sometimes. So it's just the tensor sum between phi of x plus psi of y. So I'm just going to write this O plus here to denote this. Therefore, just to write that the dual problem in the continuous setup is just this pair of dual. You could call them test functions. And this is why it plays a role. They will play a role also, for instance, there was a talk yesterday again about the Stein method, and it was mentioned that we have integral probability metrics that take a supermem over a class of functions of the integral of the difference of two measures. Here it's a more generic setting because we don't have necessarily just one test function, but we have two of them, one for each measure. Now, I don't have the time to go into the details, but this plays an extremely important role. It's a very well-known result in linear programming duality. There is a very important relationship that links whatever better coupling you might come up with here with whatever better test functions you might come up here there. So you will have in linear programming the primal dual relationships, which more generally can be called KKT conditions, but here it's a bit simpler than KKT conditions. And here what this says is that if the coupling that you will find here has mass on a pair of points, x0, y0, then this is equivalent to having a saturation of the constraint between the first dual variable function here and the second dual function here at that pair of point x0, y0. So if this has positive mass somewhere, then this is actually attained. This is an equality. Now, if you remember the synchron algorithm, I told you that the dual perspective is actually a bit easier to handle. Well, it turns out that even in this case, in the continuous setting, even non-regularized, it's also true that the dual problem to compute Wasserstein distance is a bit simpler most often. And so why is that? And we'll try to show you a bit by a teaser why it's actually interesting to look at the dual problem. The dual problem tries to find, as I said earlier, two functions, phi and psi, that maximize this integral, and have this kind of property, that link them. It turns out that for some particular cases of cost, this relationship here that links phi and psi can have surprising consequences and actually lead to very nice results. So one of them, which I won't have the time to describe today, but you might be aware of it, is this case where the cost function is the Euclidean distance between 2 points. So arguably one of the simplest setups, and probably the most geometrically intuitive setting, where basically the cost is just the length of the path between 2 points. Well, it turns out that in that case, this thing, which sounds quite complicated because you have to integrate two functions that are linked everywhere, substantially simplifies, and it just becomes this notion of computing the supremum over all one Lipschitz functions of the integral of phi against the difference between mu and nu everywhere on the support. So if you've seen this, if you've heard about the Wasserstein distance linked to this supremum of phi Lipschitz functions, one Lipschitz function, it's thanks to this duality theorem. There is another duality theorem that I would like to use very quickly here, which introduces this Brognier theorem. So to walk you through this, I'd like to just give you a hint of what is the magic ingredient that helps you go from here, from this result, which is quite complex, to this knowledge that you might have heard about, which is Wasserstein between two measures. If the distance is the Euclidean distance, it's just simply a supremum over Lipschitz functions. Well, the magic ingredient here is called C-concavity. And let me explain a bit where it comes from. Imagine I'm solving this problem. This is the dual problem. It has two variables. And a bit in the spirit of this synchron algorithm, imagine I am fixing one of those two variables. Imagine I fix phi, and I'm only focusing my attention on finding a good psi. What do I need for psi to be good? Well, there's two competing things. One is I want psi to be as large as possible. That's clear. I want to maximize. This is a positive measure. Psi should be as large as possible. What prevents me from having a psi that goes to plus infinity, though, is the fact that for every point x and y, I need to have this constraint to be satisfied. So of course I can't let psi go as much as I want. However, if I know that this is the only thing that I need to comply with, if this is my only requirement, then it's very easy to think that if for every y I just need this to be observed for every x, this is going to be the case for every x, then I would choose the largest as I can. And what is basically the largest thing I could choose here? It has to be the infimum. Because if I go across this infimum, essentially there will be a pair of points x and y for which this is no longer valid, and therefore I have ruined my constraint. So as long as I basically stay here, lower than this infimum, I'm safe. And since my interest is to make it as large as possible, I will pick that infimum as my possible value for psi. So in other words, if I freeze phi, I cannot get a better psi than this function here, which I call the blue transform of phi, which is at every point y, it's going to be the smallest, of cxy minus phi of x. So in other words, this is nice because I have simplified my optimization problem, because I have convinced you that for every phi that I choose, I can get the best possible blue function here. And this is basically this phi blue bar. And so I can only basically parameterize this problem as a function of the red function phi. This sounds nice, but this is a bit, why did I start with the red function? I could do the same thing with the blue function, right? So I could introduce this kind of red transform of a blue function that does the same thing, but the other way around. Now, I can start playing this game. I choose a red function, I get its blue transform. For this blue function, there is no better red function than the red transform of itself, etc., etc. So I can imagine, an iterative algorithm where I'm computing those transforms on top of the other. Of course, this is just a game, of the mind, because I haven't told you how to do this. But suppose, I could have access to this. Well, it turns out that this game stops very quickly, because you can prove that after applying this transforms twice, or 3 times, sorry, you fall back to the thing you had at the first iteration. Okay, but that's not a problem, because what this allows me to say is that I can already start with a function which itself is, a transform of another, whatever other function. So for instance, if I'm able to describe what makes a function C concave, so a function is C concave if it is itself the red transform of any blue function, a bit like the Legendre transform, a function is the Legendre transform of another. So I'm going to limit myself to a space of functions that are themselves the Legendre transform of another function. Then I'm already doing some progress. So, and of course, if phi is C concave, it's the same thing as saying that there exists a blue function such that it is the red transform of the blue function. And this is equivalent to saying that basically this is basically the blue-red transform of phi is itself. So this is a bit the idea of C concavity and why it's useful. Now, I'm going to be a bit fast here, but I would like to give you the gist of this. Given a cost function C, what can I say about C concave functions in general? Now that I can restrict myself to C concave functions, is there anything useful that I can say about them? Well, the first thing I can say, I'm not going to prove it because of time, but it's not that difficult to prove, is that if the cost is the Euclidean distance, then you can show that this, that if the cost is Euclidean distance, you can show that the function phi has to be 1 Lipschitz, and its blue transform has got to be minus itself, which basically explains this Wasserstein duality. I am going to prove something a bit quickly, but I'm going to prove something a bit more useful for the remaining minutes, which is that if we are in a situation where we have a cost which is translation invariant, and it is a function of the difference between 2 vectors, then you can, of course, instantiate the primal. This is the classic, Wasserstein distance. You can instantiate the dual. This is again the result of what I just told you just a few slides earlier about restricting our attention to, let's call it H concave functions. But then there is a proposition that I would like to make, which is that the optimal transport, this sounds a bit like out of nowhere, the solution of the Monge problem, the best possible map, has got to be of this form. It's got to be the gradient with respect to H inverts the gradient with respect to phi, this is the solution here, of X. So let me just go a bit or gloss over this proof. It's going to be in the slides if you want to look at it. It basically follows from these first order conditions that I mentioned earlier. But what it essentially gives us, I'm going a bit fast, but it tells us in the end that this T star, this optimal transform map, has got to be the gradient of a convex function. And it has got to be the gradient of a convex function that you can recover as the optimal dual potential of this continuous optimization problem. So let me just try to, obviously I don't have the time to finish some of the slides that I was planning on, especially with respect to this, the applications of all this. But let me try to give you here at this point in a few minutes what are current research directions in this area. The mathematics, this is the Brogniet theorem, they tell you that you should look for transportation maps that are the gradients of convex potential functions. In essence, whenever I'm going to apply the gradient of a convex function to a set of points, I will move them in a way that is optimal. It's an optimal displacement. As a result, if I am trying to estimate optimal transport, it's a good idea to focus my attention on convex potentials or the gradients of convex potentials. However, it's not so obvious to parameterize convex potentials in higher dimensions. So here, neural networks come to the rescue, as you would expect. And how does that happen? Well, they come to the rescue with respect to by parameterizing a meaningful enough family of convex functions. And so those convex functions are called input convex neural networks. And let me try to explain, and I will close on this, what they do. So input convex neural networks are a recurrent, they're a family of recurrent neural networks. So what do recurrent neural networks do? They start with a hidden state which is initialized to 0. And then at every iteration, they inject the variable x along with the hidden state, make linear transformations, and then do a nonlinear activation function. And then in the end, we recover whatever is left of the hidden state. So let me just try to show you graphically how this works. I have a hidden state z0. This could be zeros, initialized to whatever I want. I have an x here. This is my input. This is what I want to compute, a convex function on. I will multiply x by a linear operator to get a vector. I do the same thing with respect to z to get a vector of the same size. This is a linear operator again. This gives me a vector, and I run it through a nonlinear activation function, element-wise, and I get another vector. I do this again and again and again. So this is really like a recurrent neural network. And in the end, however, because I'm parameterizing potentials, of course, I want this to be a real value. So I'm going to, my latest matrix, if you want, is just a column vector, and the latest column vector for the hidden state, and column vector for the input value. And I'm again going to apply a nonlinear activation, which, if you follow here, it could be pretty much anything. It could be different at each iteration. Well, what I claim is that if all of those nonlinear activations are increasing and convex, and all of those matrices here are non-negative, then the end result of this is what Brandon Amos and co-authors in 2017 proved. The end result here of this is a convex function of the inputs x. If you follow a bit the construction, what it's doing is every time I'm injecting a linear function of x, of course it's convex. Every time I'm putting it through element by element a increasing convex function, it remains convex. This is a very simple basic principle of composition of convex functions. And then the fact that I'm mixing those hidden vectors which all contain at their level convex functions of the inputs with non-negative weights keeps convexity. So in a lot of the works that people have been doing recently in optimal transport, they leverage this type of structure to get something that is a convex function of the potentials. So I will probably have to, I'm sorry, I have had a few other contents on this and inverse GKO and things like that, but I will share the slides, of course, so please please contact me if you're interested in that part. So to sum up, optimal transport was defined late 18th century, redefined or relaxed in the 20th century. What I try to convince you is that some of the ideas are really interesting if you want to keep this notion of matching points. But if you want this to work at scale, be statistically more meaningful in the sense that it doesn't overfit data, be differentiable in the sense that you want to have a meaningful notion of changes of that matching with respect to inputs, then we need to regularize. One regularization that works quite well is the synchron, regularization. Everything related to synchron is very well implemented in this toolbox that I mentioned, odds-jacks. And please, I would love you to give it a try in your applications. There is a more recent route to really scaling up those computations, which is using this low rank assumption on the scalings. And I tried in the end, I'm sorry for the brief presentation, that using some fundamental results that come from really this Brognier theorem that characterize quite well what optimal transport maps look like, we can narrow our search, when we look for maps that transport measures optimally to gradients of convex potentials, and it's possible to parameterize such convex potentials using neural networks. Thank you very much for your attention. If there's any question, I'm happy to take them. I know we're a bit over time, and I'm the only one standing between you and lunch. Yeah, so I didn't go through some of the results, but for both regularizations that I listed here, entropic and or low rank, you show that you achieve a parametric rate of 1 over square root of n. And of course, the secret is in the constants, and the constants will depend typically on the entropic regularization strength. And so those will scale with dimension. So essentially, if you go epsilon, let epsilon go towards 0, and you recover the true optimal transport, that constant will blow up with dimension. So in a way, there's no free lunch, but what we can show is that if you want to compute this entropic regularized optimal transport, that has a much better sample complexity. For the low rank synchron approach, we have so this was an AI stats paper in 2019 that I co-authored with Aude Genevet and other co-authors. And then for the low rank approach, we have a NeurIPS paper coming up next month, what basically analyzes the sample complexity of low rank synchron. And this also depends on it's also a parametric rate. And again, this depends on the rank. So essentially, I think it's very intuitive. You're trying to optimize something that is less optimal. So in a way, you're looking less at the data, but adding some constraints. And of course, this helps a lot in terms of sample complexity. So the intuition is validated by those theoretical results. Thank you for your question.
I have a question about the low rank.
Yes.
Transport. So you have the non-negative low rank factorization, right?
Yes.
But to the best of my knowledge, there are issues of like non-uniqueness.
Yes. So
basically, my question is, do you know that for any...
Could we please use the microphones? Thank you.
So do you know that any transport map that is low rank and has the prescribed marginals has this decomposition that also has these marginals within?
Yeah, so this goes a bit to the answer earlier. I think no, there will never be an optimal. I mean, unless you go for really pathological cases where there's lots of redundancies in the distances. So a lot of points are close, have the same distance profile and others, typically when they collapse. But in general, no. I think really, if you think about the Monge map perspective, it's almost bijective, right? It's going to take X to a point Y, and typically you should be able to compute the inverse of that Monge map. So somewhat there is an extreme in the optimal transport world where you really want things to be one-to-one. And here what we're saying, both with the entropic approach and this low rank approach, is that no, actually, this is too much to ask. We can pull data together and make things collapse a little bit. And so in that sense, you will never recover, even in the limit, a solution that would be low rank with actual densities. It only happens in pathological cases. So the intuition here again is not that we want, I think there's a fundamental misunderstanding, is we never really want to approximate the true optimal transport with those sample-based techniques. What we want to do is do our best with the data, with those samples, to have something that is actually not overfitting. And then the other route, which is kind of orthogonal, which is, okay, let's look at the Monge problem. What happens in the optimum? It's a gradient of a convex potential. Well, let's use that knowledge to guide, our estimation of Monge maps. And in that case, it's the same. Although it's orthogonal, you're also trying to address the fact that we have limited samples to try to come up with a meaningful answer. So because we have many limited samples, it might be good to reduce the space of maps that you look into gradient of convex functions, which is a significant, smaller, significantly smaller set of maps, basically.
I see, thank you. Another quick question about that. So you had that middle small R by R matrix.
Yes.
Why do you need that in the decomposition? Can't you just absorb it somehow into the left and right matrices?
Well, if you absorb it, then you don't have basically you can't absorb it in the sense that you don't have the right amount of mass.
I see.
So you need to somewhat, go scale and rescale, basically.
Okay. Interesting. Okay, thank you.
Yeah, maybe G is basically on both cases, it's in the simplex.
So you would not be able to otherwise construct a low-rank decomposition that has
Yeah,
the
I don't think
marginals?
so. Yeah. Well, of course, you can absorb square root of G in both ends. That's something you can do. But then you have to add the constraint that they match. So this is a bit of a constructive way to have that observed.
Okay, thank you.
In the synchron algorithm, you implemented as matrix vector products against that matrix K, and the K is fixed.
Yes.
Is it possible, for example, like you mentioned it was like a block coordinated descent, and linear, like if your problem is completely linear, which it isn't, but supposing it was, then block coordinated descent is essentially equivalent to like a diagonal preconditioning or like a diagonal splitting or operator splitting on your matrix. Is it possible to, like, for example, either do like some sort of preconditioner idea for your K, or like, for example, in the Gaussian process literature, there's that huge thing about needing to invert the training covariance matrix, right? So there's this huge literature on doing like sparse approximation or low rank approximation or Nystrom approximation to your kernel matrix, and you mentioned that because of that, like e to the distance over gamma, that like for certain choices of distance, then it looks like a kernel matrix. So I was wondering whether you could speed up synchron that way.
Yeah, so I'm trying to unpack because there were lots of things there. So the first comment you made is, I think you were talking about preconditioning, but this would apply if you want to invert the matrix K or solve a linear system with K, right?
Yeah, like you're solving, like you're doing this fixed point iteration, which is essentially like, or I guess the way I see it is like, you can use equivalent block coordinate descent for linear systems. In that case, it's like equivalent to a preconditioner.
Okay, I'm not sure I follow you here, but what I follow you there is the kernel. The kernel part is an interesting question, and this has been studied quite a lot. And so there's here what I would basically, I think the important thing to follow here. So here I have the slides. Ignore for a second, please, the exponent. So this is a synchron algorithm. One of the issues that we have with, I would say, generic low-rank factorization of kernel matrices is that we need the product KV there in the bottom to be strictly positive, even with the approximation. And so if you look at, for instance, Nystrom methods or like low-rank decompositions of kernels, they approximate the kernel with respect to, let's say the Frobenius norm, which is okay, but that they cannot guarantee that the approximation will return something that is positive. So let's say K is more or less equal to AB, okay? It won't guarantee that AB times V is always strictly positive if you just run Nystrom algorithm or Cholesky decompositions or random Fourier features or things like that. So there's a challenge there, which is the fact that we're using this in the denominator, the kernel times vector in the denominator, and we really want this to be positive. So there are a few workarounds. So there's a few papers where people have tried to look at this. I can point you to some references. I have one of them in Europe's paper in 2020.
Thank you.
Thank you.
I'm curious if you know any examples where optimal transport has been done with an asymmetric cost function,
Excellent
and
question.
what sort of trouble would be likely to arise in those cases?
Yeah, so this is an excellent question, and really shows that optimal transport is a bit like an octopus. You know, it's like some of the solutions might work in most settings, but some of the solutions really hinge on some properties. So as I very briefly showed, for translation invariant costs that are more or less symmetric, well, could be asymmetric actually also, we have those decompositions. To my knowledge, first, in terms of applications, I don't want to, like this, you know, forget about a big application that makes sense. I haven't come across asymmetric cost that often. If you were to solve it for an asymmetric cost, though, the synchronous algorithm works perfectly fine. And I would even say the low rank approach, for instance, would help you solve this very well as well. It doesn't really build on the symmetry of the cost. So that's not a big issue. Of course, the other thing is like this Bonnier theorem as such would not work because it's a squared norm. But even this h, you know, when I showed this h function in this problem, here the only thing I told you is that h was strictly convex, and so it doesn't necessarily need to be a symmetric function in RD. So as usual, you will be able to use less, you know, of what's available. But if for your problem you have a good use case where the cost is asymmetric, I think that would be very interesting, and you would still be able to use many, not all, of the things that I've presented. Okay, I think we're done. Thank you very much. Thanks a lot.